Welcome students to the MOOC's lecture on statistical inference. This is lecture number 15. If you recollect, in the last lecture we talked about three properties, namely unbiasedness, consistency and efficiency. We are talking about minimum variance unbiased estimate, and we have introduced the Cramer-Rao lower bound. What is that? That if T is an unbiased estimator for some function g theta of the parameter of interest theta, then under regularity conditions variance of T is greater than equal to g prime theta whole square divided by expected value of del theta log of L, which depends on theta whole square, and this quantity is called I theta, named by R. A. Fisher. Today, first I will solve a few problems on efficiency or on minimum variance unbiased estimator. Then I will introduce another important property of an estimator, namely sufficiency. Okay? So, some example first. Consider Bernoulli P. So, P is the parameter of interest. Suppose I have taken sample x 1, x 2, x n are samples, independent samples. Our aim is to find the minimum variance unbiased estimator. For P. So, what we do, observe that If x follows Bernoulli P, then x takes two values, 1 with probability p and 0 with probability 1 minus p. Therefore, we can write the PDF or the PMF as P of x is equal to p to the power x 1 minus p whole to the power 1 minus x. So, check that if x is equal to 1, then this is p to the power 1 into 1 minus p to the power 0, therefore, this is p, and if x is equal to 0, then this becomes 1 and this gives you 1 minus p to the power 1, that is 1 minus p. Therefore, LP of x1, x2, xn, that is the likelihood function of the sample x1, x2, xn when the parameter is p, is equal to product of I is equal to 1 to n p xi 1 minus p to the power 1 minus xi is equal to p to the power sigma xi into 1 minus p to the power n minus sigma xi. I hope this is clear to you, because p to the power xi I is equal to 1 to n, therefore, the power gets added, and here it is 1 minus p to the power 1 minus xi. So, when I am adding this over n of the observations, I get n minus sigma xi. Therefore, log of L is equal to sigma xi log p plus n minus sigma xi into log of 1 minus p. Therefore, del log L del p, remember that here theta is equal to p, the parameter that we are interested in, is equal to sigma xi d log p, dp is equal to 1 upon p plus n minus sigma xi upon 1 minus p into d 1 minus p dp, which gives you minus 1, is equal to sigma xi upon p minus n minus sigma xi 1 minus p. Therefore, del 2 log L del p square is equal to minus sigma xi upon p square minus n minus sigma xi upon 1 minus p whole square. Because this is 1 minus p to the power minus 1, therefore, for that we get 1 minus 1, and it is 1 minus p. So, here like in this place, here will be another minus 1. So, altogether there are 3 minuses, which will keep it as minus, and this is the del log L del p square. Therefore, I p is equal to minus of that is equal to sigma xi upon p square plus n minus sigma xi upon 1 minus p whole square, and we take expected value of that one. So, this is equal to, we know that if x follows Bernoulli and x1, x2, xn are samples, then sigma xi varies as binomial with n comma p. Therefore, expected value of sigma xi is equal to n p. Therefore, using the linearity, we can write I p is equal to n p upon p square plus n minus n p upon 1 minus p whole square is equal to n upon p plus n upon 1 minus p is equal to n upon p into 1 minus p. Therefore, this is my information about p that I get from the sample. Therefore, by Cramer's-Rao inequality or Cramer-Rao lower bound for an unbiased estimator of p is 1 upon n into p into 1 minus p is equal to p into 1 minus p upon n. Note that this 1 comes because in the numerator we are writing g prime p square. Here g p is equal to p. Therefore, we get in the numerator one. So, this is the lower bound for an unbiased estimator. Now, let us consider x bar is equal to x 1 plus x 2 plus x n by n. Now, variance of x bar is equal to variance of x 1 plus x 2 plus x n divided by n square is equal to n into p into 1 minus p. This we know because x 1 plus x 2 up to x n is a binomial distribution. Therefore, it has variance n p into 1 minus p divided by n square is equal to p into 1 minus p upon n. Therefore, what we find that variance of x bar is equal to p into 1 minus p upon n, which is the Cramer-Rao bound as we have already seen here. Hence, x bar is minimum variance unbiased estimator for P. Okay, let us now consider an example where regularity conditions do not hold. So, for example, consider uniform 0 theta. Here, the parameter to be estimated is theta. So, we take a sample x1, x2, xn, and we know that f theta of x is equal to 1 upon theta, as it is uniform in the interval 0 theta. Therefore, we can calculate the Cramer-Rao bound as follows. We know that one form of Cramer-Rao bound is n times expected value of del theta log f square. Here f is equal to 1 by theta. Therefore, log f is equal to minus log theta. Therefore, del theta of log f is equal to minus 1 upon theta. Therefore, n expected value of del theta log f square is equal to n into expected value of minus 1 upon theta whole square is equal to n upon theta square. So, this is equal to I theta. The Cramer-Rao lower bound of an unbiased estimator is 1 upon n by theta square. This one is coming because g theta is equal to theta. Therefore, g prime theta whole square is equal to 1 is equal to theta square by n. Therefore, for all unbiased estimator of theta, the variance should be greater than or equal to theta square by n. Let us consider an unbiased estimator for theta. We know expected value of x n, the nth order statistic, is equal to n upon n plus 1 theta. Therefore, n plus 1 upon n x n is an unbiased estimator for theta. Let us compute the variance of n plus 1 upon n x n. Variance of n plus 1 upon n x n is equal to n plus 1 upon n whole square into expected value of x n square minus expected value of x n whole square is equal to n plus 1 upon n whole square into expected value of x n square minus n plus 1 upon n whole square into n upon n plus 1 theta whole square is equal to n plus 1 upon n whole square expected value of x n square minus theta square. So, let us compute expected value of x n square. This is equal to integration 0 to theta, let the value be t. We know that the PDF of x n is equal to, so t square, and we know that the PDF of x n is equal to n t to the power n minus 1 upon theta to the power n, and therefore, we are integrating it with respect to t. This is equal to 0 to theta n upon theta to the power n t to the power n plus 1 dt is equal to n theta power n t to the power n plus 2 upon n plus 2 theta 0 is equal to n theta power n theta to the power n plus 2 upon n plus 2 is equal to n upon n plus 2 theta square. Therefore, variance of n plus 1 upon n x n is equal to n plus 1 upon n whole square into n upon n plus 2 theta square minus theta square is equal to n plus 1 whole square upon n into n plus 2 theta square minus theta square is equal to theta square into n square plus 2n plus 1 n into n plus 2 minus 1 is equal to 1 upon n into n plus 2 theta square. And we have already found that the Cramer-Rao bound is theta square by n. Therefore, theta square upon n into n plus 2 has to be greater than equal to theta square by n, which is not correct for any positive n, because n is the number of samples, and if n is equal to an integer 1, 2, 3, therefore, this is never valid. Or in other words, we have found an unbiased estimator whose variance does not obey that Cramer-Rao lower bound. The question is, why did it happen? It happens because the range of integration while computing the variance is 0 to theta dt, that what we have done, and this limit of integration is not independent of theta. Hence, the regularity condition does not hold, and therefore, the Cramer-Rao lower bound is no more acting as a lower bound for the variance of an unbiased estimator in this case. So, that is the importance of the regularity conditions, because without them the minimum variance unbiased estimator bound will not be valid. With that, I close the chapter on efficiency. We now look at another important property, namely sufficiency. The concept is as follows. We know that if x1, x2, xn are from Bernoulli P, then an unbiased estimator which is also MVUE is equal to x bar, that is x1 plus x2 plus xn by n. Therefore, if we observe, we see that the exact sequence of occurrence is not important in estimating P. Suppose I toss the coin 10 times and my observations are 1, 0, 0, 1, 0, 0, 0, 0, 1, 0. That means, out of 10 tosses, I have got 3 heads and rest are tails. Suppose another sequence is 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, and the third one is 0, 0, 0, 1, 1, 0, 0, 0, 0, 1. In all the 3 cases, we find that out of 10 tosses, there are 3 heads, and therefore, in all the cases, expected value or the estimate is x bar, then expected value of x bar is equal to 0.3. Or in other words, we notice that this sample may contain a lot more information rather than just the summation of that one, namely what is the first result, what is the last result, how many times 0 and 1 occur together, etc. All this different information one can find out from each sample. But while estimating the value of p, we do not really need any one of them. What I need is only the sum of the observations, that is the number of heads that I found in the sample. So, in other words, we can say that sigma xi is sufficient to estimate p. We do not need any other information. If I get only sigma xi, then that is good enough for us to estimate p. This is the basic idea of sufficiency. Mathematically, the definition is that an estimated t x1, x2, xn is said to be sufficient for p if the conditional distribution of x1, x2, xn given the value of t is independent of p, where p is the parameter of interest. Or in other words, if instead of p we call it theta, we can say that if t x1, x2, xn is said to be sufficient for estimating theta, if the conditional distribution of x1, x2, xn given the value of t is independent of theta. So, let us look at for Bernoulli. And we have x1, x2, xn. We know the PDF or the PMF is equal to p to the power xi 1 minus p to the power 1 minus xi for all I is equal to 1 to n. Therefore, p of x1 is equal to x1, xn is equal to xn is equal to p to the power sigma xi into 1 minus p to the power n minus sigma xi. Now, suppose the value of sigma xi is equal to k given. Therefore, probability x1 is equal to x1 up to xn is equal to xn given t is equal to k, where t is sigma xi is equal to probability x1 is equal to x1, xn is equal to xn and t is equal to k divided by probability t is equal to k. What is this quantity? If x1, x2, xn are such that sigma xi is equal to k, then the above is probability x1 is equal to x1, xn is equal to xn. I do not need to consider this because that is going to be satisfied automatically, divided by probability t is equal to k, where t is equal to sigma xi is equal to p to the power sigma xi 1 minus p to the power n minus sigma xi and sigma xi is equal to k divided by probability t is equal to k, that is probability sigma xi is equal to k. So, this is nothing but p to the power k 1 minus p whole to the power n minus k divided by, since sigma xi is now a binomial random variable with parameter n p, it will take the value k with probability n c k p to the power k 1 minus p whole to the power n minus k is equal to, you see that this cancels with this, therefore, we are left with 1 upon n c k. And if x1, x2, xn are such that sigma xi is not equal to k, then the numerator is 0. Therefore, the conditional distribution of x1, x2, xn given t is equal to k is 0 if sigma xi not equal to k, or this is equal to 1 upon n c k if sigma xi is equal to k. Therefore, we see that this is independent of p. Therefore, sigma xi is sufficient to estimate p, and this we have argued already. Show that x1 plus 3x2 plus 2x3 plus 6 is not sufficient for estimating p when x1, x2, x3 are from Bernoulli p. So, we have a Bernoulli distribution, we have taken 3 observations from here, and my statistic is x1 plus 3x2 plus 2x3 by 6. Let us call it t. Therefore, expected value of t is equal to p, because each xi is an unbiased estimator for p. Therefore, p plus 3p plus 2p upon 6 is equal to p. Therefore, x1 plus 3x2 plus 2x3 upon 6 is unbiased for p. Question is it sufficient? We see that consider the case when t is equal to half. So, case 1, if x1 is equal to 1, x2 is equal to 0 and x3 is equal to 1, then expected value of x1 plus 3x2 plus 2x3 upon 6 is equal to half. And case 2, if x1 is equal to 0, x2 is equal to 1 and x3 is equal to 0, then also x1 plus 3x2 plus 2x3 upon 6 is its expected value, or this is equal to half. Therefore, probability t is equal to half is equal to probability x1 is equal to 1, x2 is equal to 0 and x3 is equal to 1 plus probability x1 is equal to 0, x2 is equal to 1, x3 is equal to 0 is equal to p square into 1 minus p plus p into 1 minus p whole square. So, that is the probability that the statistic t is going to take the value half, but a conditional probability x 1 is equal to 1, x 2 is equal to 0, x 3 is equal to 1, given t is equal to half is equal to p square into 1 minus p upon p square into 1 minus p plus p into 1 minus p whole square, and this is not independent of p. Therefore, we see that even if this is an unbiased estimator x 1 plus 2 3 x 2 plus 2 x 3 by 6, this is not sufficient to estimate the value of p. Okay, friends, with that I stop here. In the next class, I shall do some more studies of sufficiency. Thank you.